The Rural Access Index, RAI, is a United Nations Sustainable Development Goal indicator that measures the proportion of rural populations residing within 2 kilometers of all-season roads. This study aims to address the limitations of existing RAI assessments by proposing the Not Served Rural Population (NSRP) indicator, which represents the rural population without access to all-season roads. Using multi-source open data, the study analyzes the spatial patterns of RAI and NSRP for 203 countries and explores their correlation with 10 relevant factors, including GDP, education, and poverty rates. The findings reveal significant regional disparities, with North America, Europe, and Oceania having high RAI values and low NSRP values, whereas African regions have low RAI values and high NSRP values. There is a negative correlation between RAI and NSRP, indicating that improving road infrastructure can reduce poverty rates and enhance access to education. The study also finds spatial autocorrelation and significant imbalances in the distribution of RAI and NSRP, highlighting the importance of evaluating RAI to support the improvement of road infrastructure and ensure rural populations benefit from socioeconomic development initiatives. The study addresses the lack of exploration into the correlation between the spatial pattern of the Rural Access Index, RAI, and its influencing factors. Leveraging diverse open datasets, the research proposes a new method for calculating RAI, reveals its global spatial patterns, and quantitatively assesses its relationship with pertinent factors. The study utilizes various datasets, including population data from WorldPop, urban built-up area data from the global dataset of annual urban extents, road data from OpenStreetMap, administrative boundary data from the database of global administrative areas, and socioeconomic data from the World Bank. These datasets are employed to calculate RAI and the novel indicator, Not Served Rural Population, NSRP, for 203 countries and regions. The methodology involves identifying OpenStreetMap tags that ensure automobile access and computing the values of RAI and NSRP. The RAI formula represents the proportion of people residing within 2 kilometers of all-season roads. RAI equals POP served, PO plural, times 100%, where POP served is the number of rural people residing within 2 kilometers of all-season roads and PO plural is the total number of rural people. The RAI ranges from 0% to 100%. The spatial patterns and associated factors of global RAI and NSRP are analyzed using autocorrelation analysis and inequality analysis. The relationship between the global RAI and NSRP indicators and other influencing factors is explained quantitatively through correlation analysis. The study's findings provide valuable insights into the correlation between RAI and its influencing factors, highlighting the importance of considering spatial patterns in rural accessibility assessments. A novel indicator, NSRP, is proposed to quantify the number of rural people facing difficulties in accessing road services, complementing the existing Rural Accessibility Index, RAI. The NSRP formula calculates the number of rural populations with limited access to road services. The RAI and NSRP indicators highlight the challenges faced by rural populations in accessing road services, necessitating the development of an automatic calculation method. To address this, the study proposes a method based on multi-source open data, involving the overlay of administrative boundary data and urban built-up data to extract rural population distributions. The spatial database is filtered to extract the distribution of all-season access roads in rural areas, excluding highways and elevated roads. The study then calculates the nearest distance from the center of the population grid to the all-season roads using proximity analysis, which is revised by incorporating the Digital Elevation Model, DEM, to account for elevation differences. This revised distance is essential for calculating the RAI and NSRP indicators. A spatial pattern analysis is conducted to examine the spatial autocorrelation and inequality of the RAI and NSRP indicators. Global Moran's I is employed to identify the autocorrelation pattern of the RAI and NSRP indicators, which involves calculating the overall variance of the attribute characteristics and the weighted sum of the products of the deviations from the mean. The proposed approach enables the automatic calculation of RAI and NSRP indicators, providing a more comprehensive understanding of the challenges faced by rural populations in accessing road services. The spatial pattern analysis offers insights into the spatial distributions of these indicators, facilitating the identification of areas with high concentrations of rural populations facing accessibility challenges. Analyzing inequality and correlation is crucial for understanding spatial patterns and relationships between various indicators. One approach is autocorrelation analysis, specifically local indicators of spatial association, LISA, which identifies spatial clusters, outliers, and patterns. LISA is particularly useful for understanding the distribution of Rural Access Index, RAI, and National Spatial Reference Profile, NSRP, indicators across different regions. The Gini coefficient is a widely used measure of inequality, calculated as the ratio of the area between the Lorenz curve and the line of perfect equality to the total area under the line of perfect equality. In this study, the Gini coefficient is used to analyze the distribution of RAI and NSRP indicators, providing insight into the extent of inequality. Correlation analysis is also employed, focusing on 5 key dimensions: population, economy, employment, poverty, and education. Within these dimensions, specific indicators are selected to quantify relationships with global RAI and NSRP indicators. This comprehensive approach enables the identification of correlations between local and global indicators, providing a more nuanced understanding of the complex relationships between these factors. By analyzing inequality and correlation through these methods, this study sheds light on the spatial patterns and relationships between various indicators, ultimately informing policy decisions and development strategies. The Pearson correlation analysis was utilized to quantify the relationship between the Regional Activity Index, RAI, and the National Social Responsibility Profile, NSRP, indicators, along with other influencing variables. This statistical method measures the linear correlation between two variables, providing a coefficient that ranges from 1 to 1, where 0 indicates no correlation, and 1 or 1 represents a perfect positive or negative correlation, respectively. The formula for Pearson correlation is as follows. Pearson, x, y, equals COV, x, y, sigma x sigma y. Where COV, x, y, denotes the covariance between x and y, with sigma x and sigma y being the standard deviation of variables x and y, respectively, and n denotes the sample size. In this study, the Pearson correlation analysis revealed that countries with high RAI values are predominantly located in North America, Europe, Eastern Asia, and Oceania, while those with low RAI values are primarily found in South America and Africa. The global Moran's I value of RAI, at 0.381, indicates that neighboring countries tend to have similar RAI values, suggesting spatial autocorrelation. Furthermore, the Gini coefficient of RAI, at 0.814, suggests a strong inequality of RAI on the global scale, reflecting huge disparities in regional development. This implies that there is a significant gap in regional activity and social responsibility among countries, which could be attributed to various factors such as economic status, political stability, and cultural differences. Overall, the Pearson correlation analysis provided valuable insights into the distribution and disparities of RAI and NSRP across different regions, highlighting the need for further investigation into the underlying factors contributing to these variations. The correlation analysis presented in the table on page 6 of the research paper reveals a significant relationship between the Road Accessibility Index, RAI, and various socioeconomic indicators. A positive correlation is observed with per capita GDP of the employed population, and preschool education rates, suggesting that better road accessibility is associated with higher income levels, education rates, and urbanization. Conversely, a negative correlation is found with the proportion of rural population, employment rate, and the proportion of impoverished population, indicating that areas with better road accessibility tend to have lower poverty rates and higher employment rates. The data highlights stark contrasts between regions, with European and North American countries generally exhibiting higher RAI values and lower poverty rates, while African and some Asian countries show lower RAI values and higher poverty rates. This analysis provides valuable insights into the relationship between road accessibility and socioeconomic development, underscoring the importance of investing in infrastructure to promote economic growth and reduce poverty. This study introduces a new indicator, the Not Served Rural Population, NSRP, to complement the Rural Access Index, RAI, in assessing rural accessibility more comprehensively. The authors proposed a method based on multi-source open data for calculating RAI and NSRP values for 203 countries. They also examined the spatial patterns of these indicators and explored their relationship with various factors such as population, economy, employment, poverty, and education. The results show that most countries have RAI values greater than 60%, with a total NSRP of 1.173 billion people facing challenges in accessing road services. There is a negative correlation between RAI and NSRP, but the correlation coefficient is modest, 0.195. This indicates that NSRP can be used as a complementary measure to assess the number of rural people having difficulties accessing roads more comprehensively. The study also reveals significant spatial autocorrelation and inequality in the global distribution of RAI and NSRP. Countries with high RAI values and low NSRP values are mainly located in North America, Europe, Eastern Asia, and Oceania, while those in South America, South Asia, and Africa generally exhibit low RAI values and high NSRP values. This clustering reflects the economic and infrastructure development disparities between these regions. Furthermore, the analysis shows that RAI positively correlates with per capita GDP of the employed population, and preschool education rate. Conversely, it negatively correlates with the proportion of the rural population, employment rate, and proportion of the impoverished population. The NSRP demonstrates opposite correlations with these factors compared to RAI. These findings suggest that the economy, population, poverty, and education are all correlated with both RAI and NSRP. The study concludes that further exploration of RAI could focus on whether improvements in RAI or NSRP contribute to socioeconomic, employment, education, and other development aspects. The paper provides a comprehensive framework for understanding rural accessibility and its implications for sustainable development, highlighting the importance of considering both RAI and NSRP indicators when evaluating rural accessibility. The paper discusses the impact of road accessibility on rural villages, highlighting the importance of the Rural Access Index, RAI, as a key development indicator. The RAI can be measured using new technologies like satellite imagery and machine learning algorithms, essential for understanding spatial inequality and its relationship with economic development, particularly in rural areas. The study explores various methods to assess rural accessibility, including geographic information systems, GIS, and remote sensing data, allowing for the visualization and analysis of rural access indices. This helps policymakers identify areas requiring improved road infrastructure to enhance economic opportunities and reduce poverty. The paper reviews previous studies on rural road infrastructure and spatial inequality in countries like Ethiopia, Indonesia, and Bhutan, demonstrating that improved road accessibility can lead to increased economic activities, better market access, and improved living standards. It also discusses the significance of consolidating, revising, and piloting the Rural Access Index, utilizing advanced technologies like nighttime lights datasets and statistical techniques such as the Gini coefficient to measure income inequality. The paper concludes by emphasizing the need for continued research and development in this field to ensure rural communities are not left behind in the pursuit of sustainable development, highlighting the importance of international cooperation and collaboration.